Now that we're talking about VSEPR theory, let's walk through a few more examples. So this video will have a couple. And we're going to build off of the examples that we did with Lewis dot structures and just build off those two-dimensional pictures. So when we did our picture of CH2O, we had an oxygen double bonded to a carbon. And that oxygen had two lone pairs. And then that carbon was bonded to two hydrogens as well. I think we had drawn it like this. Now, when we're looking at this, what I'm going to do is first identify where my central atom is. Right now, that is this carbon right here. The oxygen is only bonded to one thing, and both of the hydrogens are both bonded to one thing. They're all three bonded just to that carbon. And so I'm only going to identify the geometry for something that is bonded to more than one thing, in this case, the carbon. So when I look at this, I am going to hyper focus on the carbon and ignore the lone pairs on the oxygen, which is hard to do sometimes. So on this carbon, I can see that I have three atoms bonded to it. So that's 1, 2, and 3, right? And if I look at the carbon, there are 0 lone pairs. There are lone pairs on the oxygen, but I just worry about what are the things to the central atom and how are they going to be spaced around it to figure out my geometry and my shape. So I have 3 things and there are no lone pairs. And so the furthest I can get 3 things in space away from each other is 120 degrees. And so this is going to look like, now I can draw this. I'll have a 120-degree angle around this carbon. So I'm just going to evenly space these out like this. Won't forget my lone pairs on my oxygen. So each of these bond angles is going to be about 120. And this is what this shape would look like with VSEPR theory, kind of in 3 dimensions. And this one's actually easy to draw in 2 dimensions because it would be flat, right? It would just be in the same plane, separated apart. We have a name for this geometry. It's Trigonal Planar. And we're going to give you a chart of these different geometries so you don't have to memorize them. All right, so let's look at a little bit more complicated example. Sometimes there is more than one atom, and that can make things a little bit more challenging. So let's take our methane molecule that we had built, and I think our Lewis structure looked something like this. All right, so for this to translate into 3 dimensions, I'm going to recognize that I have multiple atoms that have more than one bond, this carbon and this oxygen. So I'm going to hyperfocus on these. So for my carbon, I'm going to look at the carbon and count out all of the atoms that are bonded to it and the lone pairs. So I've got 1, 2 hydrogen, and then it's bonded to this oxygen. So that counts 3 and 4. So I have 4 atoms bonded. And I don't have any lone pairs on that carbon. Now I'm going to look at the oxygen. I really did these in the wrong color. It's hilarious. We'll color coordinate correctly here. There we go. So the oxygen, I'm going to do the same trick and I'm going to count the number of atoms around it. So I've got this hydrogen 1. Now, a lot of people, when they're learning how to do this for the first time, forget to count the carbon that's bonded to the oxygen because you already were looking at it as a central atom. But it counts too, because as we move through this process, to know the geometry around the oxygen, we have to look at everything that is sharing electrons with it. So this carbon counts as well. So there's 2 atoms bonded. And we have 1, 2 lone pairs. So both of these have 4 things around the central atom. They're going to have different geometries, which is interesting, or geometry names. So 4 things can arrange around a center at about 109 degrees from one another. But we'll have different shape names because we have different numbers of atoms bonded to the central one. And so this is going to correspond for the carbon to a tetrahedral geometry. It's a big word. Whereas this oxygen, just like in water that we saw before, this is going to correspond to a bent geometry. And it's really about the number of atoms around it. I'm actually going to redraw this as now with the trying to show the geometry as best I can. So we'll have our carbon. Okay. So this tetrahedral geometry right here for the carbon tells me I have 4 things around the carbon and they're all bonded atoms. And my geometry around the oxygen is bent. This tells me there's still probably 4 things around it, but that only 2 of them are atoms. And so they have different names. And again, this is because we can only see those nuclei, not the electron clouds. Although they're going to have a similar bond angle, which is going to be about 109. You'll notice I'm using the wedges and the dashes to represent this 3-dimensional picture in 2D. Chemists are terrible artists in general. We're really good at drawing hexagons, but that's about it. And so we represent things in 3 dimensions using wedges and dashes as a way for us to all interpret each other's pictures. And so in this picture, the dash, that's line, that means it's going away from the viewer or behind the plane of the paper. This solid wedge, this is coming towards the viewer or out of the plane of the paper. And we'll get a little more experience with this using handheld models. In general, though, it's once you kind of figure out how things are arranged, it is a little challenging to keep all of the geometry names. So we have a chart here of the most common geometry names that you're going to see, especially looking at just simple organic chemistry. If there's just the 180 degrees apart will be linear. Trigonal planar we just saw, everything was 120 apart. So that's 3 things. Tetrahedral is 4 things. It's about 109.5 apart. And then these are variations on the same pattern where you have 4 things around a central atom, but a different number of atoms. So if we have 4 atoms around a central element atom, it's tetrahedral. But if one of those becomes a lone pair and we only have 3 atoms bonded, then we call it trigonal pyramidal. It kind of looks like a pyramid. And if it's just 2, like the water, we call it bent. But these bond angles, you'll notice, are all about the same. And we have like approximates on this because for any set of atoms bonding together, you'd want to look at that specifically and see for that molecule, what is the exact bond angle. There's always variation. And so you can have this chart handy to get the names of it, but we should start getting practice with thinking through the shapes without this, just based on the number of groups that are around it in the structure. And this will be really helpful as we start thinking about molecular polarity next.